This is session E20A, Efficient Lateral Load Resisting Systems for Low-Rise Buildings. We have two great speakers this morning with a really interesting presentation. Our first speaker will be Patrick McManus. Pat is a PhD and a licensed PE and SC in 10 Western states. Pat is currently a principal with Martin & Martin, where he's responsible for the design of many significant structures. So he has a lot of things to offer for us today. Our second speaker is Jason Perry. Jason is also a PE and an SC and is a graduate of West Virginia Tech and Virginia Tech. And he is a principal with Stan Lindsay and Associates, where he's responsible for the design of many significant structures, including high-rise buildings. So, Patrick? Oh, God, Jason.
Good morning, everyone. I hope you had a good time at the conference so far. As Jules mentioned, my name is Jason Perry. Patrick will be following me here shortly. But this morning we were asked to talk about the efficient lateral load resistance for low-rise structures. We focused mainly on low seismic R=3 type of systems, just for this topic to talk about just general things. So the agenda, just to give you a brief overview of what we're going to talk about some braced frame information, moment frame information, diaphragms, the use of steel joists, a composite shear wall system, and some advantages that there may be to using high seismic systems in low seismic regions. So first, start with braced frames. Generally, a braced frame is going to be the most economical steel lateral load resisting system. This is a steel conference, so we're not going to talk about wall systems. But for comparing moment frames to brace frames will almost always be cheaper. The only caveat is you do have bigger foundations. You have uplift loads that you would not necessarily have in moment frames. But if you have trying to get moment fixity, you may have some increased foundation costs there as well in moment frames. And then they can also be concentric or eccentric braces, especially in R=3 systems. You kind of have the freedom to do what you wish and make things work around architectural features. So some of the common braced frame layouts that you see, I've got little pretty pictures here. The first one is the single diagonal. You can do them all in the same direction. Have them where you can do that type of system, I guess like a K with a floor in the middle. Have an X brace, a two-story X brace system, a V brace, and a Chevron. So I'm briefly going to go over each of these with just my thoughts on both the advantages, disadvantages. But first, in general, it's optimal to keep the brace angle between 30 and 60 degrees from horizontal. If you listen to other speakers and presentations for connection designs and other things, it's oftentimes better to keep it to a 35 or 55 degree angle. So the closer to 45 you can get, the better everything seems to work out, including member optimization, connection optimization. So just keep that in mind when you're working out your braces and your column locations. Now, unfortunately, with at least in the southeast, or probably East Coast in general, your braces are probably going to be dictated by the architecture and not the structure dictating where the architectural elements are. So this is a screenshot. This is actually an office building in my parking lot at our office. And you can see I have this eccentric brace frame because I wanted to do a chevron with a concentric brace frame with a work point there, but this is the opening to the elevator lobby, so I had to pull them out. That limited me to the chevron system because I had to provide an opening. Had to do eccentric to pull the braces out of the opening, which, looking at Revit, I'm not exactly sure they did, but the building was built somehow, and I didn't get an RFI saying that they had to do a bulkhead. So, but this kind of dictated that particular brace frame. It was the most logical place for it because there were walls around it, but I was not able to do like a 2-story X or a Chevron with a concentric brace frame, so paid a penalty a little bit with the beam design or beam size. So talking about single diagonal configurations, some things to keep in mind is there's only one brace in a frame. So it does, if you're trying to work out erection costs or different things, there's only a single brace. So you only have to erect one piece, where most of the others have at least 2 braces in a bay per floor. The flip side of that is you have no redundancy. That is your brace in that frame. So if you're, depending on what your goal is, or if you're trying to minimize a brace size to get inside of a wall or whatever, it's just something to keep in mind. And usually you have larger braces than you would another system equivalent frame, just because you do have a longer unbraced length in the same bay that you may have 2 braces in. Let me go back. One more thing I want to add to this. Depending on the configuration, you can have different impacts on the beams here. So in this configuration, the lateral load is being, in this brace, is being dragged by this beam back into this brace. So if you do this type of configuration, you will have a bigger beam than if you do this type of configuration, where this just becomes more of a drag strut element. So this one is actually framed, bringing a lot of axial load from this brace to the lower brace. This one, most of that's happening, or all of that's happening in the connection at that point. So just something to keep in mind when you're laying out braces. If you don't have restrictions on how the braces are configured, this will probably give you an overall more economical, or less tonnage, I should say, frame. X-brace configuration, you have 2 braces per level, so if you're worried about redundancy, this gives you a second brace for redundancy. If you're not in a high seismic zone, you can do tension-only braces, so it's very common to see rods used with turnbuckles to keep them taut, and they can be a very efficient system. You can do a single-story X-brace, and then you can do the 2-story X, where you're kind of a chevron and a V on top of each other. One of the things on the X-brace configuration, when you're designing that, people ask what the effective length is for the compression brace. And I've looked at this a little bit, did some research, and for a non-high ductile system, so an R=3 again, I think it's safe to assume that the tension brace can brace the compression brace. So you can use an effective length of 0.5 L. That's something that a lot of engineers don't do. They'll go ahead and use the whole length, but it's something that you can look at to do. There's, as the P delta effects, if you look at it, it weakens compression members, but it also increases the stiffness of tension members. So you got tension stiffening. So when you run through it, you actually end up with the same stiffness that you would have if you did like an eigenbuckling analysis. You'd end up with the same stiffness at that point, no matter what load you have on it. A V-brace configuration, I'll admit this is probably the most least common brace that I run into, mainly because it adds a foundation in the middle at the lowest level, whereas the Chevron brace, a very similar configuration, just inverted, does not. It only has 2 foundations. This one has 3. But if you do have doors located right beside the column, this is an effective system to be able to have a braced frame in a bay with a door right there beside the column. Now this one, because you have 2 braces coming in at the middle, you would have more force in this beam, so that's kind of an impact that you have. You may have an increased beam member. And then the Chevron brace, as we talked about earlier, I had a case where I had an opening in the middle, so this lends itself well to having openings in the middle of a bay. Again, because you have 2 braces framing into the middle, you may end up with a bigger brace than if you had the X brace in it. Although I think it's least common practice, what I've seen, that when you do design these beams, and it goes the same for the Chevron, designed for gravity without the braces there. The braces will be there. It will take some gravity load, so I usually envelope it and design the beam without the braces, and then design the braces with the gravity load on it, just so that way it should not have a failure either way. So I talked about this a minute ago, but one of the things is, in general, the effective length of the brace is the brace length. So K of 1.0, if you're using that, or if you're using the direct analysis method, you just use the length of the brace. Then on these, like I talked about with the tension stiffening effects, that if this is the compression brace, you can use just the distance from that work point to that work point for the effective length. So now I want to talk about moment frames for a little bit. So moment frames, when do they make sense? A lot of times, oftentimes, you can get it with a one-story building without much added tonnage. You can orient your framing, configure your framing such that you get moment connections with minimal impact to the cost of the structure, especially if you use beam over the top with cap plate connections, and you configure those properly. I know oftentimes on a single-story building, all your girders will be running one way over the top, and you get a frame on every line without much impact to the size of the framing. Oftentimes, you have fixed base columns at the exterior for drift control. In areas with frost, Denver and Patrick's neck of the woods, I think they have something like a 4-foot frost depth, so you got 4-foot deep grade beams. So if you can engage those easily, you have fixity without much issue. But if you're in Tennessee, like myself, and you have a 12 or 24-inch frost depth, it's a little harder. You don't have a grade beam. You have a turned down slab. So if you do a fixed foundation, it's a little bit harder to detail and come up with how to fix the column. So unlike brace frames, which are inherently stiff compared to moment frames are generally governed by drift. So you need to make sure that what the drift criteria needs to be for your building. That is dependent upon the cladding that is being used. So if you're using brick or stucco, it's a whole lot stiffer than metal panels, or a whole lot stiffer requirement. Sorry about that. There we go. The wind drift is usually based upon a 10-year wind. So when you're looking at it, you base it on 10-year winds instead of the 50-year for the strength design. And serviceability is limit state. Drift is not a strength limit state, so you usually don't have to reduce the stiffness for the direct analysis method. Some good sources for drift requirements for buildings. One is the Design Guide 3 Serviceability Design Considerations for Steel Buildings. It has some good information, gives you some guidance on what lateral drift criteria you need. And then also, I believe Larry Griffiths was one of the authors of Design Guide 3. He also had a paper that's a little bit older, but I feel like has more expanded tables on some of the different cladding that you may encounter on a day-to-day basis. The other thing is if you have curtain wall system or storefront, you probably need to find out from your manufacturers, because we found that different manufacturers have stricter criteria than others and even more strict criteria than what's in the design guide, so just something to keep in mind. It's also, if you have a curtain wall building, I do recommend that you put your drift limit that you design to on your structural notes or drawing somewhere, just so that way you have something to point to when the contractor or this curtain wall guy says, well, our system can't meet it, and so, well, this is what we designed to. Hopefully that everybody would have seen that at the beginning. Usually doesn't work, but I like doing that. Then also, if you're doing wind, checking wind drift, one of the things that's now handy is the Applied Technology Council has a website. I should have put the link up, but you can search ATC wind speed map, and you can actually enter in the address or zip code or latitude and longitude of your site, and it would give you this table here, which gives you your ASC 710 3-second gust wind speeds, as well as your 10-year, 25, 50, and 100-year wind speeds. So this is very helpful when you're calculating your wind loads or reduction factors on your wind loads to look at the 10-year wind as opposed to the 50-year wind. I know AC 705, it used to be a factor of 0.74 and 0.84, I believe. I may have those off by a little bit, but now they just give it to you per your location. So, economic moment frame conditions. This is a nice sawtooth project. I do believe it's Patrick's, or his firm at least. You know, they have beams that are running with the columns. It looks like it would be very difficult to get a braced frame in. So what's the most economical way to make that a moment frame? Well, if you blow it up a little bit, you can see this column, so maybe it makes sense to stack the columns. So if you do a stacked column, you have a cap plate with your beam bolted to it, and then you put another tube on top, and then the beam on the top has another cap plate. So this gives you moment connections from the beam to the columns in both the top and bottom. So that's an effective way to get a moment connection without a lot of full penetration welds. I know at least the standard I've seen a lot is the standard detail shows the beam flanges full penetrated weld to the columns, and that can get very expensive on a roof when you can compare to just doing a cap plate that's shop welded with 4 bolts. Now, sometimes those bolts get to be 1.25 inches, $4.90 to get some of the moment in, but it's still cheaper than doing a lot of welds, in my opinion. You could probably ask an erector or fabricator and they'll tell you something different, but I think that's intuitive to me. So on a typical single-story building, this is what our office will do a lot of times. You have a column, cap plate, we'll give the thickness, we'll give the number of bolts and the size of the bolts, and with a single stiffener over the middle. This is for an HSS column. For a W-shaped column, especially a 10 or 12-inch column, we'll have 2 stiffeners instead of a single stiffener. And this is what it looks like in the field. You have the 4 bolts, the beam over the top, so you can see they just had to bring this beam out, sit it on the top, and do a 4-bolt connection. Now, if you're doing a continuous line of frames and to get continuity between multiple beams, we'll come out a certain distance. Usually try to hit about the inflection point for gravity loads. What that allows us to do is that moment connection no longer needs to be the full moment strength of the beam. It may be a fraction, maybe 50% of the moment capacity, and then you can do a partial penetration weld for the top flange. We usually do that because of deck interruptions, and then the bottom flange can be a bolted flange plate or partial penetration weld there as well. So when you get into moment frames, you know, Optimum sizes it if drift controlled, because 9 times out of 10 a moment frame is drift controlled. One of the things you can do is get stiffer elements. Well, the easiest way to do that without impacting your tonnage is to use bigger columns. So if you can use an 18-inch or 21-inch column or 24-inch column even on a 1-story building, you're going to get a whole lot more efficient shape than if you would use a W10. So this is actually an example. I have an 18-inch column. This is a tall story. It's a powerhouse for a hospital. And they didn't have much restrictions on the floor plan. I was able to get a larger column in. Unfortunately, most reality is, can you not fit the column inside of my architectural wall? I have a 3 5/8 wall. Please make it work. Well, then you have to educate them on why that doesn't work. So you compromise. You know, W10s are used a lot. HSS 6x6 tubes. I've seen 4x4 tubes. So you end up with a lot of different things depending on where you are, how close to the coast you are for wind speeds, or if you're maybe in the middle of Texas where winds are low, seismic's low, then you end up with the smaller tubes. And so this is also another example showing that this girder is running over the top of this column. There's a splice back here closer to the next column over. So we try to limit those beam lengths to about 50 to 60 feet, what fits on a truck easily without getting a special permit. So we'll talk about column fixity. We mentioned that in deep frost areas that you'll have a 4-foot grade beam. There's details you can do with headed studs or different things to get the moment into the grade beam. Well, if you don't have that, you're shallow frost, you may end up with a base plate that looks like this. Now this is actually for about a 6-story building, maybe in Florida, I can't remember, but you can see we have a lot of anchor rods. And that's trying to get the moment into the foundation. What you don't see is that's probably a 15-foot square foundation buried in the ground. But that was the only effective way to get the drift to work on this particular building for us. We looked at pin bases, and the tonnage just shot up, especially at that first level. And so we said, well, let's go back and look at what it would take to make fixed foundations work and how big those foundations need to be to get the bearing pressure and everything to calculate out. So that kind of talks about the two frame systems that we were talking about: brace frames, moment frames. Now I'm going to talk a little bit about diaphragms and just the impact that they would have on your lateral load resisting system in a low seismic region. First of all, at least common for what I see, is the diaphragms the floors are concrete filled metal deck of some sort. So whether that's a non-composite deck with concrete on it, a composite slab, or whatever you have, it's usually some type of concrete filled deck. The roofs are usually metal roof deck, either type B or type N, and usually base your diaphragm capacities off the Steel Deck Institute deck catalog or ICCES report or ICBO report for people that's been around for a while. The diaphragm design manual is a great resource. It has a lot of information in it. It has a lot of tables that are non-manufacturer specific. Then you can also look at, like, the manufacturer of Volcraft is probably in the Southeast, 9 times out of 10, your basis of design for most engineers. And so the capacities are based on this. Just I'm questioning how often some of the diaphragms get checked in some buildings. I know we like to check them on everything, but we do a lot of work all over the U.S. and do stuff in high seismic regions as well, so it's kind of ingrained in our process that we check diaphragms. But I've heard other firms, I'm not going to say that they check diaphragms. I hope they do, but I'm not going to guarantee it. Some capacity rules of thumb. So when you're looking at your frames, one of the things, a lot of healthcare work, we do a lot of healthcare work. So a lot of times we have 1.5 B deck with a 6'6" maximum span. That's essentially a lot of healthcare companies utilize the factory mutual global data sheets for insurance purposes. So if you look at that, the deck spans are limited to certain amounts for what they've tested for wind uplift. And for an 1.5 B deck, you're around 6.5 feet. So generally that's kind of our max spacing for 1.5 B deck. So I use that. 22 gauge is kind of the minimum gauge I feel comfortable with. I would say our standard for 50 years has been the 5/8 puddle weld with a 36-4 pattern. And so that's kind of where I start. We do allow Hilti pins or other manufacturers' pins, but they need to show that it complies with the comparable strength and stiffness that the 5/8 puddle weld has. So if you run through those numbers and you look at the catalog, you're looking at about 335 pounds per linear foot in service loads. So when you're laying out your frames, if you calculate your base shear and kind of look at what each frame has, that gives you kind of a lower bound deck capacity for your roof. If you want to go what I feel like is probably on the upper end of what you'd want to specify, not saying that what you can or need to in some places, but go to an 18 gauge deck with a 36-7 pattern. You may see that a lot more on the coast with high uplifts, at least in the non-seismic zones. We see it often in like Memphis and Charleston where you have high seismic as well. But you're closer to the 943 pounds per linear foot. So when you're laying out your deck and you got base shear for your frame, that gives you an idea about how long of a collector element you need. It also gives you an idea of if your diaphragm is going to be able to span between frames. So talking about aspect ratios, ICCES reports may contain span and aspect ratio requirements. I know the building code has it for wood, but I have not seen a building codified requirement for metal deck. Until I was preparing this presentation, I didn't realize that there was a limit, but some manufacturers have it in their ICC report. So if you're doing diaphragm design, it may be worth looking to see what deck you're specifying and seeing if they have it in it. Based on the report, and I'll show you a table here in a second from one, it seems like a 2-to-1 is a good rule of thumb. You can go more depending on your frame flexibility, but that's just kind of a good layout of a 2-to-1 aspect ratio. And then obviously the deck span and aspect ratio will affect the lateral load analysis, whether it's a rigid diaphragm, a semi-rigid diaphragm, or a flexible diaphragm. So this is actually, it's a Volcraft report. It's ESR 1227, and they give the flexibility numbers. And then it also talks about maximum diaphragm span for masonry or concrete walls. So it gives that for if you have a concrete or masonry wall, that depending on your flexibility factor, which you have to calculate out your deflection of your diaphragm, to determine this, are 200 to 400 feet. Then it continues to give you concrete or walls, so rotation not considered a diaphragm. To me, that means that you're doing a flexible diaphragm analysis and you're doing tributary areas to your frames. Then here are your aspect ratios. A 2-to-1 or is required by deflection for walls, 2.5-to-1 if you're in this area for your flexibility factor. And if your flexibility factor is actually pretty stiff, you can get out to a 5-to-1. I'm sorry, 3-to-1 for walls. Then you have flexible walls. Well, how does that relate to steel? My interpretation, I could be 100% wrong, but the way I kind of rationalize this, that masonry or concrete walls, kind of rigid, that equates to a braced frame in my opinion. And if you have moment frames, you're closer to a flexible system, so flexible walls. So if you have moment frames, you can go to up to a 5-to-1 aspect ratio for a metal deck at the roof, compared to if you have braced frames, you're a 3-to-1. Then if you feel that your deck is stiff enough that it be treated as a rigid diaphragm analysis, that kicks you over into this other table. So I know some software programs have limitations and it's not easy to do flexible diaphragms. So a lot of buildings I think get kicked into this category whether they should be or not. But it's something that I would think that engineers need to look at and see if the analysis assumptions in the program with the diaphragms, rigid or semi-rigid or flexible, match what you think reality is. So at this point, I'm going to turn it over to Patrick to talk about a few other things, and thank you.
Thanks, Jason. Hey, I have one question for you that I didn't think of till I was watching you go. So when we run into issues on large buildings or where the aspect ratio isn't great, sometimes we need extra diaphragm capacity. And so we will decrease screw spacing, like even down to 3 inches in areas to increase that before we'd ever go to a welded side lap. Does your office do something similar?
We've done that in the past. I would say it's less. We usually increase the pattern to 36/7 first, and then switch over to increasing the screws. So yeah, those are just kind of what I feel are optimum, maximum. It's not, you can get a lot more out of the deck, but I like to keep that reserve capacity when I'm laying out the frames for when I actually get into the design. When I'm sure I'll forget something when I'm doing preliminaries. So when I get into the final design, I want to have some reserve capacity so I didn't realize I have to have frame later.
So just a rule of thumb, programs like I think Simpson's got one and Hilti Profis will give you capacities with much closer screw spacings than what's in the catalog if you find yourself in a bind, which sometimes we do way later than we should have. So I'm going to talk about a number of things that I think are a little outside the box of what we usually deal with and run into. They seem to be becoming more common. So one is back to primarily single-story construction, the use of joists and moment frames. So we run into a number of building types that are manufacturing facilities. We did a dairy, just a lot of jobs where really they don't want any brace frames anywhere in the interior. So you don't have much of a choice but to look at a moment frame system, and quite often they're pretty tall ceiling heights. So you're pushed into, for the economy of the system, you use joists at the roof, and now you got to figure out how to use those as moment frames. So a few things along those lines. One, fixing the end of joists, actually for the cost of the joist itself, creating that continuity isn't much of an impact to the joist. You know, you've got a joist that originally was sized or picked for WL squared over 8. To deal with wind uplift, it's usually bridged, or always, to brace the bottom chord in some fact, we hope, right, if it got installed, to brace the bottom chord anyhow. So actually fixing the end, because normally unless you're into really long joists or joist girders, you never splice the chords. It's one continuous chord, and you have generally constant moment capacity along there. You don't take much of a hit to your joist design. Where you do take a hit is the connections of how to achieve that at the columns. And so that gets a little nasty. A lot of the time in low seismic, the gravity moments that we're dealing with govern dramatically over the lateral moments. You know, we're spreading the moment from lateral to every column, so those are pretty modest. The gravity moments, when you make those joists continuous, particularly with relatively long spans, are large. So you have to make the decision of, am I trying to connect that and carry all those forces through the column, or can I decouple the gravity and create some continuity through my joist without having to push all that through the connection and just take the lateral moments into the column itself. And so one thing I'll point out is that SJI gives you a lot of guidance on this. They have some great tools if you haven't seen them, and I've just given an example of a couple here. So on the left, you know, this is just one of their guides to their spreadsheet, but this one in particular is for moment connections to the strong axis of wide flange columns. They also do it to weak axis, they do it to HSS, and that's what you're seeing on the right. That's actually the spreadsheet for an HSS. They have a lot of great tools that really help and a lot of details for that. So if you haven't seen those, they're very useful. They give you a nice guide on how to use the spreadsheet and then a nice spreadsheet to use, which is great. But then in reality, I run into conditions all the time where their picture-perfect details aren't quite the reality that I'm faced with. So quite often in the types of buildings that we're talking about, we have joist girders in one direction, we have joists in the other direction, and you have to carry moments in both directions to get those through. So that's what we have going on here. And so figuring out how to do that can be a challenge. This was a job of a very large manufacturing facility where the joists are, I mean, they're all deep. They're all at least 4 feet deep. And we had some pretty big loads on a lot of these, and kind of unusual, but because of the mechanical, we actually had a bottom chord bearing condition at the bearing. Doesn't really matter if you switch that, you'd still have a seat. But what I really want to talk about is kind of how we look to get a lot of those forces through there. So again, our gravity moments were very large, and so we had large chord forces associated with that. So if we look at the top chord, what we had is a continuity plate that basically gets you across the column to create that. And so this weld, you know, that carries the maximum load from your load combinations. And so we can transfer that chord force across. The connection of that plate to the column is really designed just to take whatever component we need that we're trying to get into the column to deal with the lateral, which was really small, like on the order of 1/10 of what we were dealing with our chord force for gravity. So that's what I'm talking about with sort of decoupling it. And yeah, you could probably go through a lot of gymnastics on relative stiffness. It's more of an ultimate strength-based approach. Now, what complicates it is then in the other direction, we have joists sitting on top of all these joist girders where we have the same issue. They're not as big, but it's the same issue. So again, we have a plate on top of here to get our moment through. And one thing that you'll run into is you might say, well, why didn't you just utilize this and design the seat to take that axial load? Ask the joist manufacturers, and they get pretty grumpy when you try to take pretty large axial loads through the seat because it cranks a moment into the chord of their joist that they're not excited to design for. So they will typically dictate that you make an attachment to those outstanding legs so that it's more concentric to their chord. So in this case, our gravity chord force, we carry in that plate that's connected up there, but then the attachment of that seat to the cap plate and to the column there actually was again designed to deal with the lateral force component that we were carrying through there. And we also specified that to the joist manufacturer that, hey, this one is eccentric to your seat, you need to design for this much anyway. But we got rid of your larger load. Okay. So that's how we handled the top. One concept, obviously there's a heck of a lot of ways to go about it. The bottom, even more complicated, right? Because you don't have a nice continuous cap plate necessarily that you can put over it. So you're either putting a bunch of stiffeners in the column and carrying very large forces through them, or you're looking for a way to really take it around it. So in this case, and this was all design build, working with the contractor and the fabricator, what we opted to do as a team was to create these plates that we essentially took the gravity chord force around the column. And so, you know, we had to design this for the eccentric loading and the bending that occurred at that interface. These plates are not, they're actually two plates, one each side, so they can sandwich around the column. We didn't slide them down over the top. But that's how we decoupled the moment in that location. So again, this weld here, sorry, if I get it off my arm, this weld here is for the full chord force. This weld here that just connects to the column, all that's dealing with is again the lateral component that I needed to get into the column. And in this case, that's the lateral component, you know, through your load combinations and how they combine for the two directions. From both the joist girder and then the joist in this case, we were connecting it to this plate, and that actually fished around to load the column so we could actually get it into the flange where it needed to be as well, because that's another thing to consider. Whenever you're loading a wide flange column and weak axis, you got to get the load to those flanges somehow, right? So again, a lot of ways to skin the cat, but in the end, this was far more economical to decouple and carry those gravity forces around the columns than to try to carry them through. And in a lot of these buildings, I mean, we literally had hundreds of columns with this condition on the job. So taking a little time to figure out how best to do it was well worthwhile. All right, a little more general discussion, and this is leading into talking a little bit about shear walls and alternates to that. So I'm sure all of you get fought with trying to save cost to your structure, especially when the project comes in and it's over budget, and the architect's response is always, all right, I'm going to go back to every subconsultant tradesman I have and tell them they need to take 10% each out of their job. Figure it out. It's like, well, cut scope. They don't listen to that very well. So what I really want to talk about or drive home here is what do we really have control over in cost, and where are there opportunities to save cost and get projects to go well? The structure in most of the projects we deal with is about 18 to 25% of the total construction cost, right? That's foundations, all the concrete, all the steel system, and the exterior structural cladding system, not counting curtain wall, light gauge studs, I guess, in our case. So structural steel usually accounts for between 10 and 12% of the total. It's a pretty big chunk. You know, it's roughly a third of the whole structural cost. But on a total for the project, that's not all that large. And then the general rule of thumb is for your structural steel costs, roughly a third of that cost is the material, roughly a third is the shop labor, and roughly a third is the erection labor. Obviously varies by project, varies by region a little bit, but it's a pretty good general rule of thumb. So if I do a bang-up job and I go in and I find a way to save 5% on the overall tonnage of the project, that equates to a whopping 0.2% on the project itself, right? And the problem we fight is that we know general contractors, their pre-con guys, and cost estimators usually price everything on unit costs. So it's not that we're just taught least weight is least cost in school. That gets driven to us because that's how it's priced in our everyday world. And it's not reality. So the importance here is, again, anytime you can get early involvement and get real numbers from the guys who are actually building the steel frame, then you can make decisions about, hey, is it really worth saving weight here, or is it worth saving complexity and keeping weight or even adding weight to reduce our steel costs? So that's kind of what I want to talk about. So weight-based decisions don't bring you the savings that they are perceived to. So in our firm, we've really started to take a little different approach to how we try to address economy. And so we're really looking at the cost of reducing cost of items beyond just structural materials. So what am I talking about? The biggest thing from my point of view is to avoid problems. If it goes well in construction, it is usually a successful project. So if you can reduce the number of trades, reduce the sequencing, reduce the time on site, that's great. Just as an aside, outside of just regular design responsiveness, boy, nothing gets a GC up in arms as to when you take more than 24 hours to respond to an RFI, right? And in general, a lot of these things are just going to reduce schedule. Time is money. If the GC is on site for less time, guarantee it saves the project money, no matter how they have priced it or presented the cost. And by that same token, like I said, to me, a successful construction means a successful project. You can, without digging myself into a hole, probably butcher the design to some degree. And if it gets built very efficiently, no one's any the wiser. They believe that it was very successful and was done well. So think about constructability in everything you do. That leads us to shear walls and why they're a pain in the butt, in my opinion. So in our region, we're a little unusual in that we have a lot of steel frame buildings that have cast-in-place concrete cores. And the reason that we've gone that way is because the GCs have told us that that's how they want to build it. In most regions, if you're steel, you're using brace frames, and if you have concrete cores, you're a concrete building. And but I definitely do see this hybrid, and it's for a number of reasons. So let's talk about some of those. The advantages of cast-in-place walls, they do have high lateral stiffness. We have jobs that demand that because we have sensitive equipment in the building that isn't just a vibration issue vertically, but it is horizontally as well, and they really need that stiffness, more so than even what they believe they might get from a brace frame. It's durable. There's a perception of good acoustical performance. Many of you may know that AISC produced a design guide, I believe, last year that really talks to acoustics. And really, concrete is a hard surface that sound goes through just fine. What you really need for the acoustics you find is to basically create a dead space between them. So that's more of a perception than a reality, but it's still there. Inherent fire separation, absolutely, you do get that. And then there's inherent flexibility for elevator supports in that you can expansion anchor or put things almost anywhere, right, within your elevator cores. The real reason in our region is that they like to self-perform concrete even when it's a steel building. And I had a GC tell me that they can increase their profitability from 2 to 3% to as much as 8% by self-performing the cores. So they're making that decision for a pretty self-serving reason, even if it's not what's necessarily best for the project. So we've tried to look at ways to watch out for that. Because what are all the problems we have with concrete cores? Well, for one, you almost introduce another trade. The guys who build foundation walls and footings, a little different crew and equipment really than the guys who go above grade with cast-in-place concrete. It's always critical path. You know, it's got to come out of the ground first. It's got to be there so that the steel can attach to it. There are pretty significant sequencing issues if you get over 3 stories. And what I mean by that is that usually you can go up and brace things back to the ground or have a self-contained core up to about 3 stories. If you start going over that, unless it's a true self-contained core, you can't go any higher before now you have to start building some steel before you can go up again with concrete and brace it back to that steel. So when we get over 3 stories, that's the first thing I bring up is, have you guys thought about this? How are we going to do it and how are we going to sequence it? Because now you can only build so much wall before you got to get some steel and then bring your trade back in and you have people over the top of each other. I think we all know there are tolerance issues. Concrete's tolerance is not great. far more lenient than our other trades. So what that means is that we end up designing very expensive, flexible connections with a lot of adjustability that usually involve field welding, which is arguably the most expensive process in steel construction. I doubt many of you are saying let's field weld every steel-to-steel shear tap that's out there. Yet we do it for concrete. And then I have never done a shear wall building that hasn't had a mist embed. Anyone here? Okay. I was going to say, I've never had anyone say they have. So the other thing is that to get the forces in cast-in-place construction from diaphragms back to the wall, we normally end up putting a bunch of form savers in that wall so that the formwork can go up. Those are pretty expensive. They're like 5 times what just a bent bar runs. They look easy to draw, but they're actually fairly pricey. And so the point is, these issues are present on every project. And in our firm, we get tired of fighting with them and about them, and the issues going back and forth of when things don't work out and things don't fit up and there are delays, you know, whose fault is that and why is it occurring? So some solutions. Composite walls are something to consider. So composite walls are covered in AISC 341, which are the seismic provisions. Don't let that freak you out. They're just there because they already addressed the special systems in there, and so really that was the only document or place to also address the ordinary system. So ordinary composite shear walls are also covered in 341, but the requirements for those walls are very consistent with just an ordinary reinforced cast-in-place wall. They're virtually analogous. So there really isn't too much that's ugly about that. But in that document, they illustrate many configurations that people have thought of over the years. I think a lot of the reasons these aren't gaining legs is because we've tested them, the behaviors well, we've thought about the system, we've drawn up concepts for them. In some cases, we're encasing columns. In other cases, we're keeping the column outside of the concrete. In some cases, we're doing the rest of it almost as standard cast in place. In others, we're wrapping this with steel plates, and AISC's got a pretty big initiative right now where they're looking at filled concrete walls where you basically have a steel plate form and no reinforcement in it. It's pretty slick. And then you have others where we're utilizing steel plate and more or less scabbing on some of the concrete to get fire ratings and all the other performance that we're after. Some of the issues with these is admittedly a lot of the interfaces at the floors haven't been thought out, and I know Jason's firm does a fair bit, and there's a fair bit of gymnastics to figure out exactly how this is going to get built. How does the sequencing work? Am I building concrete that is dependent on the steel frame again, such that, all right, now I can put my columns up, but I can't put my floors in until I've poured part of the wall? Some of those things need to be thought out and figured out and aren't necessarily addressed or contained in this document because it's just talking about seismic performance. The other thing is a lot of these do end up using steel plate. Well, big steel plates that go 4 to 4 and a lot of the time have to be spliced in the field, not something that everybody's used to or has the expertise to handle. So I think there's a lot of potential here, but there's more work to be done. One of the systems that we have looked at and are actually doing on a 4-story job right now, pretty big higher ed job, is to use Shotcrete composite shear walls. And so in this particular case, our whole intent is that the steel goes up in its entirety, and then those guys can get off site, and the shotcreters can come back and start spraying Shotcrete to create the concrete matrix, if you will. What's great is that you don't have fit up or interface issues. All the connections for the steel are steel to steel, just like building a steel frame. No sequencing issues for the same reason. No form savers because really where we do have mild reinforcing in those walls, we don't have form work really because they're using Shotcrete. So you can have bars that just go directly from the diaphragm slabs into the walls. And what's nice is if there's an issue, you can weld it. Jack Peterson, who I've worked for years, just as an aside, used to have my favorite quote about precast concrete. He said, it's got all the disadvantages of steel and concrete. It's not continuous and you can't weld it. So we can say that at AISC. No promotion of precast here. All right, so to talk a little bit about what this system looks like, what we're essentially doing is we're taking a composite slab on deck assembly and we're turning it vertical and using it as a wall. So very similar process where you put steel up, the deck acts as a form, and you pour it. We're doing that vertically. We put steel up, we put deck vertically to act as a form to shoot the shotcrete against, and then you come back and you shoot the shotcrete later. One thing I'll note is here we were just showing welded wire fabric. The R value on this particular system is something to consider because the R value, initially we had looked at it thinking, well, why can't we just call it an R of 3 system and use essentially diaphragm values and be on our way? Well, the R of 3 system in ASC 7 is very specific to steel systems. It's steel systems not specifically detailed for seismic. So what we went to is we actually put a mat of welded wire, sorry, not welded wire fabric, a mat of mild reinforcement in here, just like you would a traditional cast-in-place wall, so that you meet the reinforcement ratios of ACI 318 that is required of ordinary walls within AISC 341. So we're going entirely up with steel beams and columns, and we are using them to transfer our forces from diaphragm into the walls and walls into boundary elements. And those force transfers occur through standard headed anchor studs or deformed anchor studs. The deck is acting as a form, using traditional reinforcement mats, just like we said, and then we come back with shotcrete. One thing to be aware of in shotcrete, as you use reinforcement, the spacing requirements are greater. There's a lot of limits and issues on those, particularly when you get to thick walls and double mats that you need to pay attention to and fall a little outside of cast in place. But the whole point is that these are all traditional processes. These are all things that all of our steel fabricators and erectors are used to doing and placing on any steel job. We're just using them in a different way. So here's a little picture of the shotcrete process, but here's kind of what we're describing. So a few items with this system. So what we've got are the beams are offset of the wall so that the shotcrete can create a continuous wall through there. The reason we needed to do that is we still had to achieve a fire rating. And so if we stuck this steel in here, then we don't necessarily have enough cover or create the assembly of our UL rating that we had before. The reason we don't just keep the beams separate is because what we don't want is a deformation compatibility issue where in the final condition this wants to deflect under load but the wall's rigid and you're tied to it and they're fighting each other. So we intentionally engage this or encase this in the wall. Now, one thing that's kind of interesting about this is if you can sort out the sequencing of your job, if you know the shotcrete's going first, this beam can be pretty light because it's just holding the deck, right? Because then they're going to have this wall in place before they put all the weight of the slab and everything else on it. In our case, we didn't know that. They weren't sure and couldn't decide if they were going to shotcrete first or pour decks first. Turns out they are going to pour decks first. So then this beam had to be designed for the weight of the wet concrete until it was in place. So just like any other composite beam, really no savings beyond that because composite beams generally aren't governed much by live load. You kind of get that for free. So this is sized to carry the wet weight of the concrete. They'll pour the slabs, then they'll come back and shotcrete. So any live loads that are applied are now just transferred into the wall. But that's why we've broken this up directly. Some goofy things that we ran into, as you would expect, there were plenty. It's easy to draw the simple conditions, but when you get to all the corners and all the other stuff, I realize this is probably difficult to see. But one issue that we had is in working with the architect, they had a pretty strong preference of which side's concrete and which side's deck. And it wasn't always the way that we wanted it. And the really annoying thing is in the end, they covered it all up with studs and drywall. So it's like, geez, guys. That would have been good to know. So in this case, they really wanted the deck on this side, but our steel framing in is actually on the other side. So we essentially ended up with a double row that's hard to see. So we've got a steel channel over here that's got studs that will engage the concrete that carries all our steel. And then we had a channel over here that just allowed us to break the deck at the floors so that they could install those sheets kind of the way they wanted to. And then, we have conditions where you actually do frame through the wall and need to pay attention to how exactly your fire assembly is working when that occurs. So that is in detailing now and under construction. So before we sell it much more, I'll see how it goes and we'll report. Anyone used a system similar to that? The Shotcreter, that's the other thing I'll say. The Shotcrete guy we have in our region is on board. It's Advanced Shotcrete, and they're probably one of the top 5 in the nation. But I would say you need a good Shotcreter who has done something like this, and we had a lot of guidance, and they're obviously interested because it's a above grade market. But I think it's a great way to avoid a lot of the issues in structural steel and still achieve the benefits of a concrete wall system if you need them on a particular job. I'd have rather just gone with brace frames, but we had a huge lateral stiffness requirement and a number of other issues that drove us the other way. So the last thing I'm going to talk about a little bit is a little bit of it's something we've actually dealt with for many years because being on the edge of the Front Range in Denver, we're generally low seismic, but you don't have to get far up into the mountains before you're at least into moderate seismic. And then we actually do a lot of high seismic work as well. So we face the gamut a little bit, and that has led to some interesting issues. So one place where I would say it's worth considering high seismic systems in low seismic areas is where you have spread footings or you're dealing with poor soil. Now, let me back up a minute. The rule as far as steel costs, for sure, if you're seismic design category A, B, and C, you should be using an RF3 system. No question as far as steel costs. The whole point I'm going to make here today is that if you consider just beyond the steel the overall cost, that may not always be true. Now, the hard thing is that, again, GCs are terrible about considering the foundation costs. They like to compare a structural system to a constructional system, and the foundations are independent of that. I think the steel industry fights that on a lot of things because we design very light buildings that probably have tremendous foundation costs, and that doesn't get factored into the whole cost equation on the decision. So in these particular cases, there are some advantages that I'm going to illustrate. So footings, if you're trying to stay with footings, or if you have poor soil, a deep foundation system in poor soils, this can be a consideration. So let's talk about ones we would never use. If you are in a low or moderate seismic area, these particular systems will not provide you any benefit. Ordinary concentric brace frames, the R is 3.25. That is just almost no benefit over an R3, right? Very similarly, OMF, you're just getting very little benefit. Intermediate moment frames, your R starting to get up there to where you're reducing your forces, and it might make some sense. And these are nice because you don't have strong column, weak beam provisions like you do in special moment frames. But the reality is the connections for these are going to push you into all the pre-qualified connections in AISC 358, which are qualified generally for both intermediate moment frames and special moment frames. And so A, they're expensive, and B, in low seismic areas, you probably don't have people with experience or expertise in those, and their costs are going to be really large to cover that. So I would stay away from those. And then steel plate shear walls, same issues, usually not a great option for low rise, even in seismic areas. By the time you design the boundary elements and deal with the moment capacity in those elements, those are pretty large, so it's a better high-rise solution. But again, you're dealing with big plates and a lot of field welding to splice them, and a lot of expertise that people in low seismic probably aren't going to be experienced with. So I am not promoting at all that you would consider any of these in a low seismic area. Some things you might consider, however, EBFs have an R of 8. just like Jason talked about, a lot of the times these are a pretty good option when they stick a big door in the way, want a corridor, things like that move you into those. Now, the link is expensive. It usually has a lot of stiffeners in it. People who aren't used to dealing with those are really going to ask what the heck you're doing. But it's an option, particularly if you've gone to one of these other systems, but now you got a corridor where you just need something, so you need it at a frame or a location. SCBFs are a 6, so it's still double what you had at an RF3. So you're going to reduce your seismic loads by half at the foundations. However, the anchorage gets expensive in these, right? I mean, there are a lot of rules and protected zones and a lot of things that will be a little unfamiliar to the fabricator, but we see them built even in our region fairly frequently. But the problem is when you design the braces for these, it's driven by compactness and it's driven by the compressive capacity of the brace, which means that you end up with a brace that has way more actual area than what you would need to carry it in tension. Then you got to turn around and design your connection and the anchorage into the concrete to develop all that steel in tension. And those end up to be, I mean, you can have a brace that's designed to carry 100 kips and all of a sudden your connection has to carry 400 or 500 kips very easily. So that's the thing to watch out for on those. And then BRBFs. These are highly efficient. You're back up to an R of 8. One of the nice things is you don't suffer from the same overstrength. Their overstrength is pretty limited. They're going to size those cores generally for what you need to carry the seismic loads, and then you develop the expected capacity of those, which is pretty reasonable. The downside is they're proprietary. They're generally not great at loads less than 100 kips. Not that they don't put them in there, but even if you tell them I need one at 30 kips, you're probably getting a 100 kip brace. So might be challenges with costing, though they're fairly affordable, which we'll illustrate a little bit. So let me just run you through a couple of case studies so that this isn't all just pie in the sky. So we looked at a job that we had that was low seismic design category B. We had designed it out using an RF3 and just taking a look at one frame. So here's our base shear to the building. It was 490 kips. If I switch to an R of 8 system, you can see I cut that down tremendously, right? Now, you could be getting to a point where wind loads start to govern again. But what we have found in general is that even in our region, and we have some relatively high wind loads too, particularly when we get in the mountains, is that in the long direction of the building, seismic still governs. So it usually governs at least in one direction. If it is clad in brick and stone, which is very common in our region, that drives up your seismic mass so much that seismic still governs a lot. So this actually pans out in those conditions. So on this particular job, we had, they had put rammed aggregate piers in because the soil was pretty poor. And so we had a pretty good bearing capacity, 6,000 PSF. We were on spread footings, and so our RF3 design for that came up with this at this frame, right? 14 by almost 30 feet, and it was a big tied footing to get it to work because the overturning was pretty great, and it was hard to get a lot of dead load on it and all that fun stuff. By 3 feet thick. Again, we have frost issues in our neck of the woods, but you still needed that just to get enough dead load to deal with the overturning. So we got about 46 cubic yards in that footing, okay? If we look at an R of 8 system and we redesign it for that, we're down to 21 cubic yards, 54% reduction. If I look at an in-place concrete cost, including formwork, bar, all that stuff, this is somewhat representative of what we're seeing in our region at the moment, but Denver's pretty hot. You're potentially lower in other areas. That equates to $12,500 in savings. So you have that to offset your steel costs. Buckling restrained braces, for example, you can get them for close to $3,000 a brace, somewhere in there in general. And again, speaking in generalities on the numbers, it's just to illustrate. It'd be best to get the GC involved in this decision, which we actually did in the next one that I'm talking about. But generally, you could go or you could pay for a fair bit of steel in that one frame with that to where it may make sense to use seismic, and we're talking about a low seismic area. Here's the example we see a little more frequently. So this is a moderate seismic area. We had seismic design category C. Again, we were on pretty poor soils, and the whole intent here was that we needed to stick with or keep a spread footing foundation system. So on this job, our firm went to an SCBF with an R of 6 because it essentially cut our foundation loads in half. You can see what our base shear was under that. If I went back and looked at the R of 3, they were that large to the total, and again, that's total base shear, that's not to the one frame. Just to illustrate, so this is the system we designed, and it was specifically with the input of the GC, and they agreed that that foundation savings was well worth it for them. In fact, it was almost impractical to try to design a footing system without that, unless we look to put in a lot more frames, which architects never seem to like, as much as I try to get them to. So then for illustration purposes, I'll just show you what that base shear looked like if we actually used an R of 8 system. We would drop down to 310 from where we were at the R of 6. Okay? So again, going back to our foundations, in the system we used, the R of 6, that footing had about 45 cubic yards, which at that $500 a yard in-place rate results in $23,000. Now, the problem, like I said, is that we had to develop each of those braces into the foundation, and the GC did not anticipate what that was going to look like. And how could they? I mean, we definitely needed to give them some guidance on that. But they were a little surprised by that. Still felt it was worth it. But you can see that that inverted V was dramatic. And at each column, it was almost every bit as bad because that's where you had the overturning forces. But if we look back at what it would have been under our R of 3 system, boy, we had a 51,000, almost 30,000 higher in that one frame just to get that foundation to work. And that, just the physical size, was almost impractical. If I try to equate that back in steel terms, what that dollar amount is worth, if I even looked at a in-place steel cost of about $4,000 a ton, which probably should be more for high seismic, however you want to look at it, just for illustration, I could add 120 PLF to the weight of every one of my braces, and it would still make sense. I had that much to play with. So clearly the savings to the foundation easily were offset by the cost of the steel here. If I went and we had it to do over again and looked at BRBs, I could actually, even over my R of 6, decrease my foundation by another 31%, and I wouldn't have the anchorage issues that I did because the BRBs are a little more efficient in that. But again, it's proprietary. So just to summarize on that point, for the steel costs alone, absolutely go with an R of 3. If you are on footings or you're on poor soil, there are places where it may make sense to consider a high seismic system even in a low seismic area. And with that, I think we're done a little early, Jules.